Welcome back. Exciting class again today. I can't tell you how much I'm excited to get through Model 5. But that being said, anybody have any questions from last time? If you remember last time, we started going through changing priors, working with stand codes, seeing results of a linear model. Questions, thoughts, comments? Nah, everything's good. It's all good. All right. Well, then I'll just get started. I need to reload a few of the packages that I didn't have before. Let's just make sure I have the right data here. And then... Uh-oh. Diet data not found because I didn't change my directory. There we go. Don't worry, I will not run all the models from before. I'll just get down to model 5 here. Okay. There we go. As you remember from last time, we built this model syntax where we stand syntax, where again the model, to me the model section is the most important. That tells you where your guide, wherever all the other sections get filled out with. And we left off where we had our linear model for weight, which follows a normal distribution. The mean of it is this set of, like what we call the regression part, right, with coefficients times predictors. And the standard deviation, the residual standard deviation is given in the second term for it. I had left off that because we were playing with prior distributions. And right here it looks like, hey, wait a minute, it might be easier for us to build a bit more information in a way that's a little bit more general for this to go into stand. So let's take a look at how that might function. This, by the way, is sort of a precursor into the next lecture, which is this lecture 03B right here. That lecture 03B will be more of the same of how to write more efficient stand code. But right now, if you were to build stand, the thing I just showed you is very much specific to the example that we have, right? We have a dependent variable we call weight. Well, if we don't, how many regression models have you run where you're predicting weight? I'm guessing not many unless you've been in class, right? So we want to make this more general, a little bit more general, so that if you're running a bunch of linear models or you're changing, more importantly, if you have, maybe your outcome's weight, but if you have a bunch of, if you're running a model building sequence where you're adding or removing predictors as you go, every time you want to add a new predictor, every time you want to remove a new predictor, you're going to have to make changes to your stand code, and then you're going to have to recompile, and that gets very tedious. So turns out we can make stand work much more efficiently for what we do. I will say this, when you're trying your own syntax to begin with, there's nothing wrong with the code we developed before. In fact, if you're getting used to stand, it may be even easier to start with this code that we had before, where everything is spelled out in a way that you can see each of the parameters. But the next set of code I'm going to show you will work for almost every linear model. The problem is it doesn't look very easy to sort of synthesize. You have to sort of understand things at a little bit higher level. But we'll dive into that, okay? Okay, let's go to the model section first. Now let's name our outcome Y. Sounds good, right? That seems to be uniformly, almost every regression class I've ever taught or taken or seen, outcome variable, dependent variable is Y. Any complaints? Sound good? Cool. If you have a complaint, take the code and make it your own outcome variable. Call it outcome for all I care. Whatever. Right? So we have our outcome variable Y. Y follows a normal distribution. And this is where things get real short. If we could create what we call a design matrix, where we put a column of ones for the intercept and a bunch of columns for each predictor into something called X, that could be our design matrix for it. Right? So X itself could be a set of predictor values plus the number 1. And I'll show you how to do that in just a bit. But how many of you have heard the term design matrix before? Most of you have. It's a linear model concept. Once you get past the scalar version of linear model is you quickly find that if you take this matrix X and you multiply it using a matrix product with a vector beta, you end up with the same result. So beta is a vector that contains each of our coefficients. Right? And as you know, if you have, as you don't know, maybe you know, maybe you don't, if you haven't taken matrix algebra, what you should realize is matrix algebra, you can't multiply any two matrices together. They have to conform to a certain size. Right? So in fact, that size is the number of columns of the matrix that's the pre-multiplying matrix, the one on the left-hand side, has to be equal to the number of rows of the matrix or vector on the right-hand side. So here, what we end up getting is a number of persons, number of observations by number of predictors matrix, n by p is the size. That means that beta has to have p coefficients, p rows, if you will, and it can have one column. Right? So the result of this is an n by 1 vector where each value in that vector is the predicted value. Is formed by taking each person's set of predictor variables from X and multiplying those by the same coefficients in beta. So it really shortens the syntax quite a bit. Any questions on that? Okay. Turns out, now what we have to just apply to Stan will be Y, which we did before, a matrix for X, which I'll show you in just a bit, and the number of remember when we define a matrix, we have to define what its size is. So let's do this. Let's look at the code before. Y, that's similar before. It's a vector. It's our outcome. And we have to tell it how many observations there are, right? There are capital N observations in this case. X then should be the same number of N observations, but we'll have now P columns, or P predictors plus an intercept itself. So here is X. So Stan has a type of data called matrix. The type of data that are in matrix is assumed to be a floating point number. If you remember in Stan, we have to declare every variable. We have to tell it which type it happens to be. So in this case, we're saying every element of X is a floating point number. And the size of X has N rows and P columns. How are we doing so far? We also have to tell it what those P predictors happen to be as well, too. Okay? Okay. So now, that's the mean side. The standard deviation is still the same, sigma. We can leave that alone. For most of the basic linear models, unless we're doing a location and scale model, we leave sigma by itself. Then we can talk about the prior distributions for each. Right? So sigma, since I have it highlighted, actually let's talk about prior. We can go back to that exponential distribution for a prior. Remember the exponential distribution last time? Looked like a very lazy version of an L, right? The more informative the prior is, the more peaked it is at 0. The less informative, the flatter it is across the range, but it goes from 0 to infinity. And what we will say is the hyperparameter, remember the hyperparameter is the parameter of the prior distribution. The hyperparameter for the exponential distribution for sigma, we'll call it sigma rate. Let's input this, make it an input variable into Stan. This will keep us from having to recompile our Stan code every time we want to change the value of the hyperparameter. Right? If we wanted to sort of determine whether or not our hyperparameters were the right ones, if we had too informative of prior or less informative of prior. Right? So here the sigma rate parameter will show up in our data step as a real number. That's our prior rate parameter. How are we doing so far? Any questions on that prior? Okay. Now beta is our vector of regression coefficients, and they're capital P of those right there, right? One for every column of our design matrix. Now, because we have more than one of those, we're going to switch to a multivariate normal. Remember in our last example, every one of our beta coefficients had a normal distribution. Every one. in our new example, then, what we can say is every single beta will follow a normal distribution. In this case, we'll use a multivariate normal distribution to make that same set of priors, right? A multivariate normal distribution, if you haven't taken multivariate statistics, is a series of normal distributions tied together. Now, they're tied together through the use of a mean vector, so each variable's mean is in the mean vector, and each variable's variance is in the diagonal of this covariance matrix. Now, the off diagonal, you can put a covariance as well too, which is like a correlation, right? Sort of a rescaled correlation between variables. But in our case, and one of the nice properties of the multivariate normal distribution is that if we put a value of 0 for covariance, that means that the variables, any pair of variables, is uncorrelated or independent. So the prior that we put on each of the betas previously with a series of normal distributions also assumed that each of these betas were independent. They weren't correlated in a prior distribution. So when I build a multivariate normal distribution, if this covariance matrix just has numbers along its diagonal and then zeros in the off diagonal, this set of priors for beta will be the same as what we had coded previously. The only difference now is that we can make it so that this mean beta is a vector that we import into stan to talk about where each value's prior mean should be. And cov beta is a matrix that we'll import into stan, right, of size coefficients by coefficients, p by p. And that will tell us what the variance for each one of those, the diagonal of it will tell us what the variance for each one of those beta coefficients, the prior variance. So our hyperparameters are built into matrices. That's a little bit more of a complex concept, but it certainly shortens the code. In fact, this syntax that you see right here, you could teach the entire intermediate statistics course with this syntax right here. Right? One stan model, there you go. It's all the linear models that you would have. Everything else is something about the design matrix that we change. Pretty cool, huh? Just like that. Boom. Intermediate statistics. But questions on what I just showed? Question in the chat. If variance is called cov, what will be the covariance if the covariance is not 0? Well, I'm calling this, so it turns out in a multivariate normal distribution, there are two sets of parameters. There's a vector of means and there's a covariance matrix. So we refer to the second set of hyperparameters as a covariance matrix. That covariance matrix along the diagonal contains variances. If you want to think of it, why we call it variances in a covariance matrix, the variance or the covariance of a variable with itself turns out to be the variance. Kind of crazy. It's only when we have a pair of variables that we have covariance involved. So that even though it's called a covariance matrix, the diagonal of it is referred to as variances. The off diagonal is referred to as covariances. And if we can specify a prior that has non-zero diagonals, we can specify anything for a prior. Remember, a prior distribution is our belief. But here's what I will tell you. We can have a belief about the coefficients. In fact, when we put our coefficients in last time, I remember each of you are asking you, do you think 0 is a good hyperparameter to use for a mean for each of these betas? And each of you looked at like, I'm not so sure about that, right? So you have a sense of where the beta coefficients might be in terms of their mean. And you have a sense of where their standard deviation might be. Maybe one is a little more informative than we wanted it to be, right? We saw that last time. But what is your prior belief about how beta 0 and beta height, for example, might covary? Do you have any belief on that? Now remember, we're not talking about variables covarying here. We're talking about parameters covarying here. Anybody want to take a guess? I don't have a belief. I have no idea if the coefficient for the intercept should be related to the coefficient for height. No clue. So if the covariance is not 0, that just reflects that your prior belief is that these two parameters may be related. But that prior belief is just that. It's a prior belief. It may be the case that actually, if you use a non-zero covariance, you may change a little bit of the posterior distribution. But remember, that's prior. Once we grab the data, we sort of update the prior, we form a posterior. We'll play around with that in just a bit. So, hope that answers your question. Any other questions on what I've shown here? All right, then let's build it. So it turns out the first thing we need to think about, we know what n is, right? That's just the number of rows in our data set. That's the number of people we have. The number of predictors, we can count 2, right? In fact, we can go to our previous model and count those. We have 1, 2, 3, 4, 5, 6. 6 coefficients for p. So we know what those are. The hard part is x, but it turns out r makes it not so hard. There's a function in R called model.matrix. Model.matrix will take your linear model that you have here. Let me just make this a little bit easier. So here's the formula for our linear model. Right here is our formula. So now when I create this, it just shows in R there's a type of object called formula. It's sort of a very primitive or basic object. But because R is in the business of statistics, it tends to make objects out of things that are like things like formulas and so forth. But here we have weight in pounds is being predicted by height in inches, a factor variable for diet group, and then the interaction between height in inches and the factor variable. And previously, we had to form each of those values in code. Remember that? At the top of this syntax file here, I created every single one of those predictor variables. Where did it get up here? Right up here, right? Right after model 1. Right here is where we created everything. Well, it turns out this model.matrix function will do it for us. So if I run the model matrix with our formula and our data set, take a look at what we end up getting. Here we have it. The intercept, the column of ones. This is a design matrix. The height in inches, the dummy code for factor group, the interaction of height in inches with the dummy code for group 2, and the interaction of height in inches with the dummy code for group 3. That's all the data that I just created. That makes it a lot easier, doesn't it? Pretty interesting. Turns out there's a whole lot of shortcuts like that the more advanced you get with R, statistics, and Stan. It's hard to teach that way from the beginning, though. Right? We got to build up to that point, build some scaffolding in. But so questions on design matrix. Turns out, with that design matrix, the dimensions of it are 30, which is our n, by 6, which is our p. So we just have to basically build in our object, the number of n is the number of rows in that design matrix, and p is the number of columns. So there we go, we figured that one out. That one's easy. X is solved. Let's now build the matrix for the hyperparameters, though. Right? So the mean vector for our coefficients, our hyperparameters for it. I'm going to set the mean vector equal to 0 for each one of these, but I'm going to build the covariance matrix such that the diagonal of each value is 10,000. Right? That's our covariance matrix. So if you want to know what that means that I'm setting a prior distribution where the mean is 0 for each coefficient, but the standard deviation is 100. Right? So practically speaking, using a normal distribution for each, and because 0 is in the off diagonal for each of these, they're independent normal distributions for each coefficient. What I'm saying is, I believe the regression coefficient is most likely between 0 plus or minus 3 times 100, or somewhere between negative 300 and positive 300. Does that seem reasonable? Maybe. It'd still be, if we knew nothing about the data, that still may be too informative. Right? We may have coefficients much bigger than that. But for right now, let's leave it like that. That sound okay? In Lecture 3C, I will teach you a method to where you can have these hyperparameters be estimated as well too, which may be a little bit more appropriate in linear models. I'll show you that in just a bit. Okay, finally, let's pick a value of 0.1 for that hyperparameter of the exponential distribution. If you remember from last class, 0.1 had a very uninformative prior. It was very low, right? So we'll use that. Okay, so I just put all the objects together. Now let's build the stand data list. Remember, the stand data list has to correspond to the names in the data section in stand. Otherwise, it will not run. So here, we have n, we have p, we have capital X, we have lowercase y just as our outcome variable from our data frame. We have the mean beta, the covariance beta, and the sigma rate. All those go into a list. And then we compile our model. We hope it compiles. Let's go. I feel like we need compiling music. Or better yet, when it finishes, there's like trumpets. Hey, it did. It worked. Now I'm going to run a warm-up of 1,000, a sampling of 2,000, and we're going to sample this. And it ran in 0.3 seconds. You'll note that's pretty quick, right? Turns out the matrix operations in stand work a little bit more efficiently than the scalar ones, but it still works. Let's check convergence. Let's see the maximum value of r hat, 1.001346. That is as converged as you can expect. That's really good. We could also take a look at our trace plots as well. And those look converged. See some posterior histograms and some posterior densities. One thing I wanted to compare with was our very first model. So let me go back and run our first model one more time, since I haven't done that. I'll run this model quickly and we'll compare and contrast the results from this last run with our first model because we've changed the prior distribution hyperparameters again. And let's see, back down to 05. Yes. There we go. I need to grab my summary real quick. Okay. This is a comparison of our fixed effects. So now, let's see what we have here. Remember, their posterior means look very similar. And we could figure that out. Actually, our posterior mean for sigma squared is a little bit smaller in this case. Right? So you could see this is the first three columns are from our original specification where we had uniform priors on everything. Our last three columns are from our current specification where our priors for each of the coefficients were normal with a mean of 0, standard deviation of 100, and then our prior for our residual variance was exponential with a hyperparameter of 0.1. So here you can see things are roughly similar. We have a smaller posterior standard deviation, as one would expect, because we have a little bit smaller prior on our, we have a little bit more informative prior than uniform on our exponential, but things aren't very different. But generally speaking, that looks okay. What do you think? Questions? All right. Shall we move forward? Moving forward. So let me take one drink, make sure there's no other questions. So this, yes, Vladimir. Yes, although the picture that you see on the screen, these are both from Stan. So both of these are sampling based. Yes. Okay. Yes, that's right. How informative a prior happens to be is judged by how much variation it has. Yes. Higher variation, smaller information. Yes. Go ahead. Correct. That is right. So, for instance, here in the first three columns, we had a uniform prior across the floating point number line. That uniform prior was literally, you could not get less informative than that, right? So, I mean, it's flat, so there's no difference for any proposed value of sigma. Whereas in our example we just ran, we had an exponential distribution across well, I guess both of these are on the positive numbers. I said full real number line before, but it's positive numbers. So that exponential distribution is slightly more informative than the uniform distribution, which causes our prior variance to move to the point of where that information is. And as we saw in the exponential distribution, it's centered around 0. So it forced our point estimate, our posterior distribution for sigma, towards 0 a bit. Does that help answer? Thank you for your question. I appreciate it. Other questions? No other questions. All right. Now, finally, how are you feeling about Bayes so far? Conceptually okay? Does it look tedious? Yeah, it's easy. It's a lot easier to use one command and do LM. Fair. Well, there are packages that will do Bayes and R, but I'll just leave those for you to find them because I'd like you to learn how to write the code yourself. But now we're going to get into the fun part of Bayes. All right? So when you run a linear model, you have your coefficients, but sometimes you need other quantities calculated. Right? So when we have our linear model, right, when we look at our, let me see if I can get to our formula real quick. There's our linear model. Let's take a look at this height coefficient. We call that a main effective height, right? What does the height coefficient represent? Anybody want to take a stab at interpreting? I'm going to put you on the spot. Don't make me call on one of you. I feel like I'm like having a stare down with my 9-year-old son. I'll wait. It doesn't make for good YouTube videos, that's for sure. But I'll wait. I'm asking you to interpret what the slope is for that parameter I've just highlighted. Yes, Ryan? And actually, yeah, this one right here. Yeah, that's yeah. Good start. Let's go with this way. For every 1 unit increase in height, in this case, for every additional inch. Now, 60, because we've centered it at 60, it turns out that additional inch is not involved in the centering. You can just say 1 additional inch. Whether we've moved 60 or not, it's all 1 inch. So we'd say that. So for every increase per inch, for every inch taller a person might be, weight goes, in this case, down by 0.37 pounds, right? It's units of y per units of x. So pounds per inch is what we're looking at here. However, that would be correct, but we have this interaction, right? So who wants to add on the modifier to what I just said to make it correct? JC. So that's right, for the reference group. So when the term multiplying height is equal to 0. Correct. Right? So now we're saying this is the slope for people in diet group 1 of height for weight. So let me ask this next question. How would you find the slope of height in inches for diet group 2? That's right. Thank you, Erica. The linear combination, right? So we have to think about it. If right now, if we say y equals beta 0 plus beta 1 height, or beta height. Here, I'm going to make all the... Here, you know what I'm going to do? Watch this. Put this here. There, I have all the coefficients written out. So let's just make this part of the example here, right? So if this is our linear model in total, right? What we want to talk about is the slope for height. So we're talking about this right here. So let's go and grab every variable where height appears, because height will have something to do with this slope, right? So here, height is here, height is here, and height is here. So if we take those three out, what we're left with is this plus these two other terms. Okay? So far, so good? All right? So now, if we wanted to say, okay, when do we have height group 1, right? Height group 1, or for group 1, what's the slope for group 1? Well, this value is 0 for everybody in group 1, right? The height by interaction, because group 1 has a 0 for the dummy code. Height times 0 is 0, right? So that goes away. This term is 0 for height group 3, for height group 1, right? So those go away. And so we're just left with beta height, as at the end, right? And actually, what I really should do is change the name of this, because it's technically height in 60 inches times group. And here, this is height 60 inches times group 3, right? So next, if you wanted to say, what's the slope for group 2? Well, in group 2, this term is 0 right here. So I'll just comment that thing out, right? This term is a 1. So what we're left with is the following. Beta height times 60 inches plus beta, this interaction slope, times height times 60 inches. And if we do some algebra and regroup, where did that number come from? That was weird. Here, if we do this, height 60 inches is the common term to each. So if I just pull that together, we get beta height plus beta hxg2. So the slope for people in group 2 is found by beta height plus beta height group 2, those two coefficients. Cool, right? In Lisa's version of intermediate, if you took Lisa Hoffman's intermediate, you knew the GLHT function in R to form that linear combination. And so what ends up happening in a linear combination is you adjust the mean, right? The mean of each of these, the posterior. And you have to adjust the covariance, the variance and covariance as well too, right? So in the frequentist version, there is an adjustment for the mean vector and an adjustment for the covariance matrix that gives you the result with your p-value, your standard error, and so forth. In Bayes' world, we can build that directly into our stand code so that the result, when we finally look at our result, our summary table, we might have a slope for group 2 built in. How do you like that? And where it comes from, by the way, is taking the value of each parameter, beta height and beta height times group 2, those two parameters, and adding them together throughout every iteration of Stan. I think that's pretty cool, right? So we just have to add those together to build it. Stan will do that for us. Now there are other things we may want to calculate in a model like this as well too. For instance, we may want to calculate R squared, right? Turns out there's a formula for R squared. I don't remember off the top of my head, but I'll find it, tell you about it later. The point of the matter is, though, because there's a formula for r squared that will be written as a function of the values that we have here, our regression coefficients, really our residual standard error, and something about the total variance that we have, we can have Stan build a Bayesian version of r squared as well too. The calculation of r squared such that we actually end up with a posterior distribution for r squared as well. And this is the part where I think Bayes is awesome. We can build posterior distributions for things that we would never think about before. Shall we do some of that? Want to see it? Okay. To do this in Stan, it turns out we introduce another block in Stan syntax, and that block is called generated quantities. Generated quantities is a block of Stan that will take the parameters from your model and calculate other values from them, right? Those other values can be almost anything, right? But what then happens is those generated quantities, they do not affect the model. They do not change your model. They do not change your estimates. They don't involve in anything else. They're just sort of things that you want to tabulate as you go along. So the generated quantities block looks like this. And it turns out, let's talk about our height slope for group 2. Well, if we were to import what I would call a contrast vector, a contrast vector would say which betas needed to be summed together. Then we could take it and use a matrix product and add those betas together as we go through. And let me go down to what that contrast vector may look like. This, if you took Lisa Hoffman's intermediate statistics, is the input into the GLHT function, in that this contrast right here represents the number to multiply each coefficient with to build that linear combination for the group slope for group 2, the height slope for group 2. And what we know is that in our model, the height slope is in the second position, so we put a 1 there. And the height by group 2 interaction term is in the fourth position, so we put a 1 there. And we put zeros elsewhere. So what this code in Stan does, we have contrast times beta. Each of these is a vector. So what it does is it multiplies each element of contrast times each element of the current values of beta for every iteration in the Markov chain. And then it sums them together. So what we end up having is a 1 times the second beta and a 1 times the fourth beta. The result of this shows up in a new variable called height slope group 2, and that gives us our posterior distribution for height slope. And it turns out you could create as many contrasts as you want. You could look at the height slope for group 3. You could look at the height. You could look at the difference in group, the difference in weight, for a person, by group for a person who's 70 inches tall. You could look at all sorts of different features the same way and calculate that using Stan directly. Now, technically speaking, you could do all of this with just the posterior draws later on, but Stan makes it easy to do it built into Stan, and then you get all the benefits of the plotting and the other ways of looking for it. All right, questions on that for the linear combination? No questions. Excellent. Then let's talk about r squared. R squared, you may remember, is 1 minus the regression sums of squares over the total sums of squares, right? Well, we can calculate these things as well too. Right? If we have the predicted values for every person, which really comes from our design matrix times the current value of beta from every step of the chain, then the regression sums of squares is y minus the predicted value squared, or in this case, dot self is sort of a dot product with itself. A dot product is a matrix term. The total regression, the total sums of squares is y minus the mean of y overall, right? Your y minus your mean of y, sort of your value for it, squared. So r squared is 1 minus that ratio. And at the end of our chain, we'll have an R2 that shows up in the summary. One small note about this syntax, you'll note here in my brackets, I put the, I guess these are braces, braces around this section means that each of these intermediate steps in the calculation will not be saved in the output object. Right? We won't save the Markov chain for this pred right here, but we could, but we won't. Why we're doing that is to cut down on space. It turns out these Markov chains take a lot of data, a lot of memory, right? They're huge, right? 10,000 values, no big deal. But every time we compute something, it's going to add to the number of values we end up having. So here, the braces indicate that we're not going to save the intermediate calculation steps. We're just going to save r squared. And finally, in generated quantities, the values of the variables, the variables that you use in there, just like the variable you use elsewhere in Stan, have to be declared. So we have to tell it what type of variable there are and what their names are. So each of these are real numbers. Question in the chat, what does the dot self mean? Dot self is basically looking at, if you take the vector y, which is our vector of input data, and you subtract from it the vector of predicted values. So this is y minus the predicted values. This is a residual, right? Y minus the prediction. It is each element times itself added together. Or put another way, it's the matrix dot product of residual times residual. You can think of it as like a sum of squares, right? Where each element is squared and then added together. Does that answer the question? Great. Thank you for asking. And when we get into matrices, look, linear models run great on matrices. So you'll see a little bit more matrices here than you will when we get to psychometrics. But when we get to multivariate psychometrics, you will see more matrices again. So if you're not as familiar with matrices, don't worry. We've got time to get used to it. And I'm absolutely happy to teach you what I know about matrices to make things easier as well, too. Okay? All right. Should we run this? I think this is going to be fun. This, to me, is where all this stuff blew my mind when I started to work on it. Because what we're going to end up having is a posterior distribution for r squared, which means you can build a credible interval for r squared. Like your r squared is between this region. I think that's cool, personally. But, you know, let's sample. Let's take a look at our summary. Remember, before we look at anything else, though, let's take a look at r hat. Oops. Here, we have an NA value for one of the r hats. When that happens, it happens to be for total regression, total sums of squares. Now, total sums of squares, I thought I made a mistake when I said the braces. Because I defined it outside of the braces here, it's outputting. But you'll note y minus the mean of y never changes. So what that means is there's no variance in that total RSS. And because r hat is a ratio of between chain variance to within chain variance, both of those values are 0. You end up getting a 0 divided by 0 for this, which really means NA is displayed. It's actually not a number. Anything divided by 0 is technically undefined. I can't wait until they come out with a definition for it, but, sorry, math humor. 0 divided by 0 is undefined, right? So that's why you see an NA there. And if you're calculating in generated quantities, you will have that. So you may have to say, what's my maximum r hat? You may have to just remove the NA values. When I do that, you'll see our maximum r hat shows it converged. So good times. Now let's go and take a look at the actual values of this. You'll note now we have a bit of a problem because, well, we're in scientific notation. I hate that. Right. So what is r squared? Well, we knew r squared before was quite high. 9.73 e negative 1 really means move the decimal place to the left one. So our r squared is 0.973 right there. Not bad. Let's take a look a little bit more at then what I like to show here is our time series. So these are all the draws of each of those. Let's just take a look at the r squared. This is our r squared posterior distribution with histograms. That's kind of cool, isn't it? Right? This Q5 and Q95, these are not, that's not the HDPI, the highest density posterior interval, but it's going to be pretty close. Actually, this is a skewed distribution. It may not be that close, but you can see it thinks we're 90% confident r squared is between 0.965 and 0.977. I think that's cool, right? If you're like, what's my R squared? You have a variance to it. So let me ask you, quick Bayesian check. Why do we have variation in R squared? Why does it vary? Or a posterior distribution for it? So in regular frequency statistics, we only get one. Why in Bayesian does it look like this? Why do we have a variance to it? Why does it have a distribution, posterior distribution? That's very good. Distribution of possible values. Yes, that's getting there. Probably I'm asking the wrong question. But let's talk more technically to that. Here's why. Remember how we're computing it. In Stan, and the chat was least square. Nope, not quite. But think of it this way. In Stan, if I go back to my trace plot here. Sorry, you can't see this very well. Let me make this a little bit bigger. You see each one of these betas in every iteration has a different value, right? So if we just drew one sample from the posterior, let's take the 1000th iteration. We'll have a coefficient for 6 different betas, plus we'll also have 1 sigma, right? That is technically a plausible value for each of those parameters. So because that's like one result in frequentist, it's not the most optimal result, but it is a possible result because we're sampling from this posterior density of all the parameters. And so because that's a possible result, what we can do is take the values of each of those betas and calculate our R squared, right? As if they were the output from a frequentist value. So we could say, hey, from iteration 1000, we see our R squared happen to be this number because we know we used the actual values of each of the betas in that calculation. So where I was saying this from a Bayesian sense, and why I'm talking about this as a Bayesian question, is that what we have to think about when we draw from the posterior distribution is that any of the draws that we pull from that posterior distribution could be the true values of the parameters. We don't know. So because of that, we can use that information and create all of our summaries as if they were the true values. So for every iteration, we can do that. And once we look at everything across iterations, we end up with a plot that looks like this. Right? This is the R square tabulated across all of our posterior draws. And you can say, like, what's the most extreme values to it? Well, one of them was as low as 0.93, and one of them is as high as close to 0.98. Right? And you can see it also is very skewed, right? That's a skewed type of distribution. So again, we can use this to our benefit in calculating R squared. I think that's a cool part of Bayes, personally. I happen to like that quite a bit. All right. Similarly, let's take a look at this height slope right here. In fact, I need the name for it, so let me go grab that name. And let's take a look at its trace plot. So this is the value of the height slope for group 2 at every iteration. Remember, this was formed by taking the main effective height and adding to it the interaction of group 2 by height. Right here. So we can talk about how it varies, and then we can also look at its posterior distribution as well. So if you wanted to look at, sometimes we talk about simple slopes in linear models or multi-level models. If you wanted to build a simple slope conditional on a value, you could do that with a contrast statement. And now we talk about the posterior distribution of it. And if you want to talk about whether or not this slope Was there a significant slope for height in group 2? The answer is yes, because we can see that 0 doesn't really fall anywhere into our posterior distribution at all. Again, we could take a credible interval of this, see that it ranges between, and here, let me get the numbers again. 80.9 was its posterior mean, and our credible interval that's not highest density, which will be very similar to highest density because it's symmetric, is somewhere between 73.7 and 88.0. But because 0 doesn't fall within that interval, as Bayesians, we'd have high confidence to suggest that this height has a significant effect for group 2. That is what this is telling us right here. And we still get a posterior distribution for it as well. Now this value here is similar to what you would see in a frequentist output, because in that linear combination that we do to build our height slope, there is a very easy tractable, I wouldn't say easy, but there's one single closed form formula to calculate it based on the covariance matrix. All right. How many think that's cool? Leading question. How can you not think that's cool? Oh, maybe I shouldn't say that. I think it's cool. Now, where would you think of it? We could use that in psychometrics? I got an idea. How many of you have seen a standard error on reliability coefficients before? Now, if you go through my website and you go back to 2016 or 2017, I taught SEM at Kansas. I showed how to do that in Levon, but you have to know a little bit about factor analysis to build it. But we could do that too. So in a Bayesian sense, we can calculate so a reliability coefficient is really a nonlinear combination of certain parameters in a model. Model itself can be formed in different ways. We could use, if we were to go and use this in a psychometric sense, we could talk about how much certainty we have about the reliability coefficients that we might build this well too. Or how much certainty we might have about person parameters, the posterior distribution. Those aren't usually added together, but they could be. Certainly could be. So, questions? No questions. We good? All right, let's move on to the lecture for 03B then. And actually, what I'm going to do is stop this recording and start the next one.